Hi everybody. All right, time marches on. This is class number 2 for fluid mechanics. This lecture is intended for Thursday, the 26th of August. Once again, I apologize that we're not able to meet in person this week, but we will be back to our normal class location and normal class time and meeting face to face on Tuesday of next week. Let's go through a couple of announcements. Remember that it's important for you to get a copy of the textbook. Now, the assignments that you're going to have this semester are largely ones that problems that I myself have written. So you're not going to use the textbook most of the time for homework problems, but it is an important source of information. The author can explain things with a different perspective than I can, and so I really think it's worth your while to rent or buy the textbook. The introductory assignment, that getting to know you short answer type assignment, is due before noon on Friday the 27th, and so please upload your responses to Blackboard before then in order to get the 10 bonus points. And then looking a little bit further down the road, homework number 1, which you can look at right now on Blackboard, that should be submitted before 11 a.m. on Thursday, September 2nd. So we'll have some office hour opportunities and a chance to talk over those homework problems before you need to turn it in, but I just wanted to put it on your radar so that you can look a little bit further down the road. The topic of today's lecture is viscosity and gas laws. And so the rest of this presentation was recorded in an earlier semester, but the material remains the same. I'll just, before starting with that, remind you that although I'm out of town this week, I still would be happy to try and address your questions by email if you want to send me a message. And then next week I'll be back to my face-to-face in-person office hours.
First, I wanted to point out that next semester I'm going to be throwing this slide into my presentation. You may remember that we had a discussion about whether at the bottom of the ocean water compresses itself because of the weight of the water above the bottom of the ocean. And I thought that was a really interesting thought question. And so, I learn from your great questions sometimes. I learn, what's interesting to students and how can I be more thought-provoking. And so I'm going to throw this slide in next semester. And I just wanted to illustrate that, even though we're talking remotely right now, it still is possible for us to have a good interactive experience. And so I appreciate the questions when you've got them. It makes it more easy from my perspective to teach. Okay, now this is a photograph, and does anybody want to guess what this is a picture of? Is this
honey.
Water?
Looks like honey to me.
It looks like what?
Honey.
Honey. Good, that's right. And what are the clues that that's honey?
There are bubbles trapped inside it as it's flowing.
Good, very good. And so seeing those bubbles, what does that imply? Like if this was water, we wouldn't see those bubbles. So what does it mean when you have the bubbles?
They can't readily escape.
They can't readily escape. Good. And so there's something about this fluid that makes it so that the air bubbles can't escape. Another interesting thing is if you look at the taper, can you see my cursor? It's never clear to me whether students can see my mouse cursor. I guess you probably
Yeah, I can see it.
Okay, good. That's must be a new feature for Blackboard Collaborate Ultra, because in the spring students couldn't see my mouse cursor, but you can now. So another clue that this is not water, besides the color, obviously. Another clue is if you look at the taper there, it's kind of, if this was water, it would be going into individual droplets. The water accelerates fast enough, it speeds away from the spoon as you pour it out of the spoon, that it wouldn't be cohesive and pouring out into a sheet like this appears to be. All right, so there's something about this fluid that's a little bit different from water. Let's watch a video clip that also addresses this same issue. All right, so I have, here we go. Bring it into full screen mode here. I'm going to mute it. And all right, so fluid on the left, fluid on the right. Something's different. the person is shaking these two different fluids. They're both clear. There's the same amount. They're in the same kind of container, but when you shake the one on the left, it sloshes around easily. The one on the right doesn't slosh around. So when you're shaking the container, you're applying a force to the fluid. When you apply the force to the fluid on the left, the fluid responds to that force. And so it's deforming. The force that's applied is causing the fluid to deform relatively easily, it seems like. But the fluid on the right isn't deforming as much. You're applying a force, but it's not sloshing around. Okay, now let's see what happens if you pour it. The fluid on the left, which is water, pours easily. The fluid on the right, which is glycerin, it pours really slowly. That's thicker than honey. It's thicker than syrup. Just looks so delicious. I want to put it on a stack of pancakes. Glycerin and pancakes. It's a winning combination. So this illustrates the principle of viscosity. So let's talk about viscosity in detail. Now, to understand viscosity, we have to define some terms here. You may remember from previous courses that you've probably heard the word strain. And so strain is the deformation of a physical body under the action of applied forces. So we just saw in the picture forces being applied and the fluid deformed. But solids also can deform when you apply a stress. I wonder if I have my ruler in here. I do. Brilliant. All right. So I've got this metal ruler. I don't know if you can see the picture of me. It's probably pretty small down there at in the bottom of your screen, but I'm holding up a metal ruler, and if I press on that metal ruler, I'm applying a force right now, and it's deforming. Can everybody see it's formed into an arch? Now it's not moving anymore, it's stationary, but I am still applying a force. So right now, the physical body is deforming, and the strain is that deformation under the action of the applied force. So a solid has this proportionality factor between the shear stress applied and the shear strain. So the stress is the force, the strain is the deformation. And the relationship between the two is defined by shear modulus. So this is steel. How do you think it would be different if this was titanium? Maybe we don't know a lot about titanium, but maybe you do. What do you know about titanium compared to steel?
It's more brittle, it would probably break.
It's more brittle. It would resist the deformation. If I applied this much of a force, I think it probably would, but well, if it deformed this much, it probably would break. But just think about my weak little fingers, my weak engineer fingers. I couldn't break titanium with these little weak fingers, but what would happen is it just wouldn't deform as much if this was titanium. So steel, it deforms a lot. Titanium, it deforms a little bit. So there's this material property, the relationship between the stress that's applied and the strain that is experienced by that solid. The proportionality factor is the shear modulus. Well, there's a similar thing in fluids. In a liquid, that proportionality factor is called viscosity. And the difference between, one of the many differences between a liquid and a solid is that in the case of a liquid, it continues to deform as long as the shear stress is applied. So an example of that is if you put a propeller into a tank of water. The water is going to continue to deform as long as the force is being applied. Whereas in the case of a solid, it only deforms, it stops deforming even though you're still applying a force. And if I want it to deform more, I have to apply a greater force. But a liquid will continue to deform. And so it stays in motion as long as the stress is applied. So the reason why I compared the solid and the liquids is just so that you kind of understand that there's an analogy here. The analogy between stress and strain in the solid and stress and strain in liquid. We're going to look at some figures. I hope that will make this a little bit more clear. Gavin asks, is there still a yield stress when dealing with liquids? No, there isn't. All right, so one of the principles that one of the applications of viscosity is the fact that a river has a different velocity at the top as it does at the bottom. So we have a river here in Huntington, the Ohio River, and you maybe have noticed that when you look at the top of the water can be, it looks like it's moving pretty quickly. But if we went down to the bottom where the water is in contact with the soil, the velocity would actually be 0. So when we talk about the velocity of the river, there's not just one velocity, there's a whole distribution of velocities. There's a spectrum. And here is a velocity distribution. And what it shows is that if we are down here at the bottom of a stream, the velocity is 0. But as you go higher up and further away from the bottom of the stream, the velocity is increasing. And so up at the top of the water, the velocity is higher. And so this slope, dy dv, is just how quickly the velocity is changing with an increase in depth. So let's watch a video clip that introduces this idea that at the bottom of flow, where the water is in contact with a stationary solid, the liquid velocity is 0. All right, now this is a little bit murky. It's maybe hard to see what's going on, so I'm going to explain it before I play the video. I'm going to give you a sense of what we're actually looking at. This is a straw. So there's a straw that's going down into a flume. And most of you went into the fluid mechanics lab this week, and in the back of the room there was that big long channel. You can think of it as like a big plastic, it's like a plastic simulation of a river. So there's clear acrylic on either side, and then the bottom of it is plastic. And so you're putting water down this channel, and it's similar, I guess, to a rain gutter. Think about the rain gutters on your house. It's just a long rectangular channel that carries water. So in this case, what's happening is that water is flowing from the right to the left. No, I don't remember what direction the water is actually flowing. We'll see. So this is a straw, and it's going to be injecting a dye. And we're going to see what happens to the dye that's being injected. Okay, so they're going to put the straw down at the bottom, and right now that straw is touching the bottom of the channel. So think about it's a simulated river, and this straw full of dye, they inject a little bit of the dye. So can you see the green tracer? So they're injecting some of that green tracer, and so it's like a big blob of dye, and it's not sticky. It's a water-soluble dye, so it's not like it's glue or anything like that. But it will stay at the bottom because the velocity down there is essentially 0. Now when you take the straw back up into the rest of the stream, you can see that these ripples and turbulence kind of indicates that the water is flowing from the right to the left. And so the dye is acting as a tracer. But there's still this big clump of dye down at the bottom because the velocity of the liquid is 0. But when they put a spoon down in there and stir it around, the dye goes away because you finally put enough velocity to make it go downstream. So that's just an illustration of the no-slip condition. So the question is, can it be assumed that the farther away the liquid particle is from the stationary surface, the faster it goes? Yes. That's a great question, and yes, that's the correct observation. And this velocity distribution is kind of an illustration of that effect. The farther away you get from the bottom, where you have the no-slip condition, no-slip boundary, that just means that the bottom of the river isn't moving. The bottom of the river is stationary, and the farther away you get from the bottom, the faster the liquid is, because that solid surface down there is applying a resistance to the movement of the fluid. All right, so if we define some of the terms
Would
here,
this not be experienced on the sides as well?
yes, it would be experienced on the sides. So that was like a clear plastic acrylic on either side, and you're right, it's not just the bottom, it's any place that the water is in contact with, it's going to have that no slip boundary.
It's always true that the farther away from the stationary surface the fluid particles are, the faster they'll be moving.
Yeah, okay, I understand your point. Yeah, you're right, because for example, the spoon, when the spoon went down to the bottom and he was swishing the spoon back and forth, well then that's no longer true, that's the lowest velocity. So there are, you know, like if you have external interventions like a propeller or the spoon, then you can defy this general velocity distribution trend. Okay, so viscosity is the resistance to flow. Remember when you had that glycerin in the beaker and it was being shaked back and forth and it was resisting flow? Flow is the response to the forces that are applied, and viscosity is resistance to that deformation. So in this figure, V is velocity, Y is the distance from the bottom, which is the no slip condition, and then mu is viscosity. And sometimes we call it absolute viscosity, sometimes we call it dynamic viscosity. Those two things mean the same. Absolute viscosity, dynamic viscosity, those are two different names for the same exact thing. And sometimes we just call it viscosity. So any three of those terms are interchangeable. And it has units of Newton seconds per meter squared. The shear stress is the force that's applied per unit area. And so if you think about the units of shear stress, it's going to be force per area. And so shear stress, the relationship between shear stress, the deformation, and viscosity is this equation that's shown on the screen here. So remember what I said earlier is that viscosity is the proportionality factor between the shear stress that's applied and then the response of the fluid. So shear stress is force per area, and then dV dy is the rate of strain. dV dy is basically how quickly the velocity is increasing the further away you get from the boundary. So think about this velocity distribution. Right now, let's say this figure is a river of water. What if it was a river of pancake syrup? Well, that would be delicious. But what we know about pancake syrup is that it has higher viscosity than water does. And so there wouldn't be as steep a curve if this was pancake syrup. You'd have to go further away and maybe the velocity would just be a little bit higher. So it wouldn't be deforming as readily if it had a high viscosity. So you can think of it that way. Another illustration example is just thinking about the fluids that you walk through. It's easy to walk through air, but if you're in the swimming pool and you're trying to walk, it's not as easy. You can't walk 4 miles an hour through a swimming pool because the fluid is getting out of your way not as readily as air gets out of the way. When you walk through air, it deforms out of the way really easily. Now, if you're driving a car at 100 miles an hour, there's some serious wind resistance there. The fluid is deforming and it's applying a resistance force, but it doesn't require a very big velocity to have some resistance force through a more viscous fluid like water. So water has a higher viscosity than a gas like air. So why is it easier to walk through air? Because it has a lower viscosity. So there's less friction. You can think of it as resistance or drag force because of the viscosity of the fluid. Another way to think about it is that it's deforming at a higher rate than water can because the viscosity is lower. So back to this formula, if you have a low viscosity, then you can have a large dV dy for a certain amount of shear stress that's applied. So you're applying a shear force to a fluid, a low viscosity will give you a big dV dy. Then if it's a big viscosity, so if mu is large because it's pancake syrup, then for the same force, the rate of strain has to be lower. Air moves out of the quick rate when you apply a shear stress. Water and other liquids that have a greater viscosity will move out of the way more slowly. So here's that equation again. Shear stress is viscosity multiplied by dV dy, which is the rate of deformation, or rate of strain. So if we graph it, you can see the difference between air, water, and oil in this figure. And what it's showing is, think about this vertical axis, which says shear stress. Remember, the units of shear stress is force per area. So a certain amount of force applied to a unit area is only going to get you a little bit of deformation for oil. So here's the curve for the oil. And so for a certain amount of shear stress, the oil is just going to deform a little bit. So think about shaking it side to side in the beaker. Sloshing it around, you're not going to get as much of a response with a viscous fluid like oil compared to water. Water's going to slosh around really easily. But for a certain amount of shear stress, what would deform the most is air. And so in the horizontal axis here, rate of deformation, you can just think of this as the response to the shear stress that's applied. And so the slope of the line, you can see here that we're calling the shear stress is A, and the rate of deformation is B. And so shear stress divided by the rate of deformation is how we define viscosity. All right. So viscosity is the slope of the line if we were thinking about it in graphical terms, which means it's the ratio of the shear stress to the rate of deformation. And when we were just kind of doing some general definition terms earlier, I suggested that one way to think about viscosity is its resistance to flow, because something with a high viscosity will have a high resistance to flow. A low viscosity will have a low resistance to flow. Let's look at another video. All right. So this is an experiment where we have several different fluids here. I think it's water and maybe an oil, honey. So what they're going to do to illustrate that there's differences in the viscosity is they're going to drop a ball into each one of them. And how quickly the ball settles to the bottom of the liquid is a reflection of how easily the liquid is deforming out of the way. And so wait for it. It'll be worth it. Starting on the left, the water, dropping that marble. Oh, I think that must have been air because it looked like it fell really quickly. So air is a liquid, a fluid, right? Okay, this looks like an oil. And we could, with a stopwatch, time how long it takes for that ball to settle down to the bottom of the fluid. And so there's different viscosities and different speeds that it settles. And this one must be really thick because it is deforming out of the way so slowly. So these are just another illustrations of viscosity. And so you could characterize viscosity by how quickly the fluid deforms out of the way. Remember, terminology-wise, what we've been talking about so far is absolute viscosity, which is the same thing as dynamic viscosity, and sometimes we just call that viscosity. I'm going to introduce another term now, and that is kinematic viscosity. And kinematic viscosity corrects for the fact that some fluids are more viscous when they have a greater density. So there's kind of a co-varying relationship between density and viscosity. So a lot of equations that we use in fluid mechanics will have both the viscosity term and also a density term. And for that reason, and also to be able to express viscosity independent of a fluid's density, we sometimes use kinematic viscosity as a variable. and it's the ratio of viscosity to fluid density. So here's the formula for it. The formula is we take mu and divide it by rho. And so remember, viscosity has units of Newton seconds per meter squared, and density from our previous discussion has units of kilograms per cubic meter. And so if we cancel those terms out, remember a kilogram is a base unit, but a Newton is a kilogram meter per second squared. So if we were going to expand the units of the Newton out to its full base units and then simplify, what we get is that kinematic viscosity has a unit of meter squared per second. So it's length squared per time. So it's just another way of expressing a similar thing. So here's the terminology. Absolute viscosity, dynamic viscosity, and viscosity all mean the same thing, and we assign them the same variable mu. But kinematic viscosity is something different. It's where we're dividing that by the density. Now, shear force is when you multiply shear stress over an area that it's being applied. And so if we want to find out how to calculate the shear force for a fluid that has a certain viscosity and is experiencing a certain rate of strain, so du dy here means the same thing as dv dy. You probably already know from physics and statics and all that sort of thing that sometimes we use u for the velocity variable, sometimes we use v, but here what we mean is the rate of deformation, du dy. So the way that we use this equation, it's applied, and it's of course units of force is newtons. The way that we apply this formula is that sometimes there's a linear relationship between the change of velocity and the distance between two surfaces. And so rather than assuming a curved velocity profile, we just use a linear distribution of velocity with distance to simplify and solve some problems. So here's like a physical instance that we can use viscosity to do some calculations. Let's say that we have glycerin in a tank. Remember from one of the earlier videos, glycerin was the thing that poured out of the beaker really slowly. So what we know about glycerin is it has a large viscosity. It resists deformation when a shear force is applied. So what we have is this sheet of metal. It's a metal plate that's 3 meters by 2 meters. And so what that means is it has a surface area on the top of 6 square meters and also a surface area on the bottom of 6 square meters. So it has in total a surface area of 12 square meters. 6 on the top, 6 on the bottom. Now if we tow it through the glycerin, we have to apply a certain shear force. A force in order to get it to move through the liquid. Now what we're saying is we want to achieve 0.58 meters per second. We want this metal plate to drag through the fluid at 0.58 meters per second. And we're also given some technical data, like the glycerin's viscosity is 0.15 Newton seconds per meter squared. And then also we know the distance, that it looks like it's closer to the top of the tank than it is to the bottom of the tank. So what the example says is it's 1.2 meters from the metal plate up to the top of this tank, and then 2.4 meters down to the bottom. So what we want to know is solve for F. How big of a force is required in order to achieve this total velocity of 0.58 meters per second. So you can see I've given you a hint, is we're going to be using this formula. F is viscosity times area times du dy. And here I've said we can just use velocity divided by distance as du dy. But we've got two distances. We've got the distance to the top and the distance to the bottom. And so the total force is going to be the sum of the force on the top and the force on the bottom. So what I'm going to do is pause for a moment, give you a chance to get your calculator, piece of scratch paper, or you can solve this in the notes if you've printed those out. But I'm going to pause and I'm going to ask you to calculate F. Calculate the total force required in order to us to get a velocity of the plate moving through the stationary liquid if the plate's moving at 0.58. All right, so I'm going to stop talking. If you want to type a guess there into the chat box once you think you've got the numbers, I'd invite you to do that. That would be great. Back. We're trying to figure out the total force, and let me drag the solution over to this screen. Okay, so what we're given, we have the equation that defines force applied, viscosity, area, and rate of strain. We know the distance to the top is 1.2, the distance to the bottom is 2.4, the velocity, the viscosity, so those are all of our knowns. So if we want to calculate the force that's on the top of the plate, because the top is closer, it's closer to that location where the tank is stationary. So there's going to be a greater shear force there because the distance is less than the bottom. So you can see where I've substituted in the numbers, and the top force is 0.435 newtons, the bottom force 0.2175 because the distance is greater down to the bottom of the tank. And then the combined force when we add those two together is 0.6525. So any questions about that? All right. Well, great. That is a taste of what you're going to need to know in order to solve the homework. So, question.
Yeah, can you go over how we calculated the area that we needed to calculate this for? Because I know you said we need to do the top and the bottom, and we're doing 3 meters by 2 meters, so we have 6. But
Right.
I don't, like, why are we not just doing the face, like the surface area of the face that's dragging through the water?
Good question.
Or glycerin for that matter.
So this is the thin plate. You know, the thickness of this plate is so small relative to its top and bottom area that there is going to be a drag force having to do with like the front face of that plate, but it's going to be negligible compared to the drag force that arises due to the area on the top. So let's say, for instance, if this plate is a centimeter thick, so, you know, that's a pretty substantial metal plate if it's a centimeter thick. But still, the area of that, if it's 1 centimeter by, let's say, 2 meters deep, that's going to have a really small area in contact with the fluid compared to 6 meters of area on the top and then another 6 meters of area on the bottom. So we kind of neglect the thickness of the plate and the interface, the like vertically oriented interface, because what's going to be by far the dominant surface area is the top and the bottom. And so we use 6 as A because we've calculated the forces on the top and the bottom separately because they have different distances, because the dy is different for each of those. So hopefully that addresses your question. All right. Are there any other questions?
So what about if the plate had like a bit of convexity to it? Would we use the same type of formula?
Well, I guess, you know, if it's really convex, then now the drag force, you know, like the projected area from the front would be different. And so depending on how convex it is, we may no longer be able to like neglect that the profile drag that we did in this example. So I guess it would just depend on how deformed it is. Let me give you another illustration, and this is of a homework problem that, okay, I got a question from Harrison here. Does the formula only apply to surfaces parallel to movement? Could it be used for the front/sides of a thick-sided plate? I'd say, yeah, it does only apply to forces that are parallel to the movement. And I think that you'll get a sense for how it applies as we look at a couple more examples. Let me bring up the homework assignment here. So in one of these problems, in problem 6, you have a cylinder that's falling down through a different cylinder that has a hole in the middle of it. And so there's oil that's inside that boundary. And so that lubricating oil is, if you think about the distance, it says here it's 0.003 inches thick. So if this inner cylinder is falling downward, then you're going to be able to have the velocity defined for you, 0.5 feet per second. And so thinking about this formula that we've just looked at, that would be the du, the given velocity, and then the, oh, wrong way. Okay, here it is. And then the gap distance of 0.003 inches would be the dy. And so here's the dv, here's the dy, and then the area. So the question is about what area to use. It's going to be the area that is in contact with the fluid. And so it's not going to be like, if we think about a cylinder, I'm holding up a water bottle right now, the applicable area isn't this bottom area of the cylinder, it's the side area of the cylinder. And so in this homework problem that you're going to have, it's the area, the outside area of a cylinder is, you first of all find the circumference. So that's circumference pi d, and then the distance. So circumference times the distance would give you the outside area that's in contact with the fluid. So that will be the applicable surface in that homework problem. And that homework problem is similar to a problem that I used to give out of the textbook. In that textbook problem, which this other one is similar to, there was a cylinder that was falling down through a pipe. And so it was a similar thing where there was a gap distance. And so it's the gap distance between the two is what defines the dy. The dv is how quickly it's falling. And then the area will be the area that's in contact with the fluid, but not the top or the bottom area. It's the outside surface area where, where's the gap the smallest is going to be what governs, because of in the formula, the dy being small means that you have a much greater force. Viscosity is independent of a fluid's pressure. And so the viscosity of a fluid doesn't change if it is being compressed and pressurized. Terry asks, by nature, will the cylinders always be concentric? I'm afraid I don't know what you mean by that, Terry. So here we have a cylinder. What is it you're asking? Do you have a microphone, Terry?
Yeah. So what I'm asking is, if you have that cylinder sliding down the pipe, like by nature, like would it be the path of least resistance for the cylinder to stay exactly in the middle of the pipe on its way down?
Gotcha. Yeah, that's a great question. And I think you said it exactly right when you said the path of least resistance. And so that cylinder wants to travel at the highest velocity it can. Not that it has like conscious preferences, but it wouldn't go up against the side wall because then it would be falling more slowly. And so just in the same way that water flows through the path of least resistance, the cylinder would fall through the path of least resistance, which is going to be to maximize the distance around the edge there. So yes, it would. It would fall down the center of it. And it may like bang back and forth, but in general, it's going to maximize its velocity. Okay, so fluids don't change their viscosity based on the pressure that they're experiencing. And this viscosity arises out of the molecular forces within a fluid. And so fluids that have high cohesive bonds, molecular bonds inside of the fluid, are going to have those cohesive forces decrease as the temperature goes up. So viscosity does vary as a function of temperature. And you probably have seen that before when you change the oil on a car. If you've ever had the pleasure of sliding under a car and changing the oil, what you know is that if the oil is warm, it pours out really quickly. But on a cold winter day, if you don't let your engine warm up before you empty the oil, then it can drip out of there for hours. It just drips really slowly because it doesn't have the same viscosity. So the temperature dependency of viscosity is that in a liquid, the viscosity decreases as the temperature goes up. But ironically, in gases, the opposite is true. That when a gas temperature goes up, because the molecules are bouncing around more, since the molecules have more kinetic energy, that ends up having a slight effect that increases the viscosity of the fluid. And before we get into the Sutherland's equation, let me just show you the figure of that relationship. So this is showing the kinematic viscosity of two different fluids. It's showing that in oil, the viscosity is decreasing as it gets warmer. So down here on the horizontal axis is temperature. So with the oil, it's pretty dramatic. When you're down near freezing, the viscosity is high, but as the oil heats, the viscosity is much lower. So if you look at the magnitude of these units, it looks like about 1/10 the viscosity by heating the oil from freezing up to 100 degrees Celsius. With air, that slope isn't quite as steep. It does experience an increase in viscosity, but the effect isn't as dramatic as it was with oil. But I remember when I was growing up, there was this airplane that they wanted to do a continuous flight around the world. I think it was called Voyager. It had maybe you've seen it if you've been to the Air and Space Museum. I think they have it hanging up in Washington, D.C. It has a propeller on the front, a propeller in the back. And what I remember about that is that they did it during the winter time because they wanted the air to be cool and have more viscosity, because if the air has more viscosity, then they're able to generate greater thrust with those propellers. And so the reason why they didn't do their attempt in the summer is that in the summer the air would be warmer and therefore would have they wouldn't get quite the same thrust that they'd get in the other case. So what Sutherland's equation does is it allows you to estimate the effect of temperature changes on changes in viscosity. So it's an equation that's empirical in nature, and it just allows you to estimate if you know the viscosity of a fluid at a certain temperature. So in this example, for instance, let's say that we know the viscosity of air at 50 degrees Celsius is 1.95 times 10 to the minus fifth Newton seconds per meter squared. What if we wanted to find out that same fluid at 95 Celsius instead? Well, what we have to do is use units of Kelvin in order to solve this. And so we're going to convert both of these temperatures from Celsius to Kelvin and then solve for the mu, the velocity at the new temperature, where we start off with the viscosity at a given temperature. So this is another one of those where I'd like to pause for just a moment and give you a chance to try out Sutherland's equation, because there's a homework problem where you do this. Let's try and find out what's the viscosity of air at 95 degrees Celsius. So that's going to be the unknown viscosity at a T of 95. And of course, you have to convert it from 95 Celsius to Kelvin. And the original viscosity of 1.95 times 10 to the minus fifth was at a T naught of 50 degrees Celsius. Again, converting over to Kelvin. All right, so I'll stop talking, give you a chance to exercise your calculators, and I'll be giving out gold stars in the chat box to people who get it right. On the screen, just in case you're stalled, so that we can see where things are going with this. All right, so the first thing we have to do in this problem is convert the given temperatures into Kelvin, which is par for the course when we're dealing with gas type problems. And so our givens is that the initial temperature for which we know the viscosity, 323.16 Kelvin. The temperature where we want to know the viscosity, 368.16 Kelvin. And then we're also given the initial viscosity and the Sutherland's constant. And then you can see the substitutions that I made in there. Now, this is the first, but certainly not the last time, I'm going to point out a habit that I think is really important for engineers. And I think it's an important habit for you to be really explicit when you're making substitutions. And so in this example, what I did was I wrote the equation first, and then I showed the direct substitution for every component of that equation, including the units. It's really worthwhile to write the units when you're substituting things in, because for one thing, it'll help you to avoid mistakes of maybe substituting the wrong variable in the wrong place. You know, for example, if you write the temperature in Celsius accidentally, and so you had, you know, like 50 Celsius, and then this Sutherland's constant is Kelvin, then you'd see, oh, these are different units, I can't add it together. But if you just wrote the numbers, if you just wrote the number 50 and then the number 111, then you're not going to have that same like opportunity to recognize that the two shouldn't be combined. So in other words, what I'm saying is include the units when you write down the numbers, and you're going to make fewer mistakes. Also, it's just more professional and more neat if you include the units. And so the other thing I'll point out is that I don't try and do all the calculations in a single step. I kind of take a few steps, and so you'll notice that what I did here is I had the ratio of the temperatures, and then I write that number there before I do to the 1.5 power. And the advantage of having it in multiple steps is, again, you avoid mistakes, and you can check your work more easily. I think it's really a good habit on exams, for example, to check your calculations 2 or 3 times before you submit the work. You just want to make sure you didn't make a calculation error. And so if you do kind of like these intermediate steps, it helps to check your work. So in the end, you can see what we end up with is 2.15 times 10 to the minus fifth Newton seconds per meter squared. Any questions on these calculations? So you have, this allows you to estimate the viscosity of a gas when you don't have it like in a table. It's just a way to extrapolate. All right, so we already looked over these figures for the viscosity of air and oil, and this is a kinematic. So if you'll remember that the units for kinematic are length squared per time. There are some other ways to classify fluids. a Newtonian fluid versus non-Newtonian fluid. And what we mean by that, a Newtonian fluid is where there's a linear relationship between shear stress and shear strain. So water is a Newtonian fluid. The slope of the line is dynamic viscosity in a Newtonian fluid. But there are certain fluids that are a little bit funny. Maybe let me just show you the video clip before we go through the definitions in too much more detail. Let me first of all, let me see if I can copy that link and put it into my other browser. All right. Look at these kids walking on a fluid. Have you seen something like this before? Sometimes this is called oobleck, but really what it is it's just cornstarch dissolved in water. And so if they walk fast enough, they can avoid falling down into the fluid. But if they stop for a second, then they get stuck in the fluid. They go down into it. So this is a non-Newtonian fluid where the viscosity of it responds to the shear stress that's being applied. So let's look at this other video as well before we talk about it a little bit more. So copy link, and then I'll paste that over here. I'd love to have a swimming pool full of that non-Newtonian fluid. Oh, those golden fries. You didn't think you'd have to sit through commercials during fluid mechanics class, right? Okay. All right, so this is a high-speed camera, and that same thing, it's the cornstarch water mixture, and they've added some food coloring to it in order to make it more visually appealing. When you apply a force to it, then instantaneously the viscosity of the fluid changes. Like if you're not applying a force, it has a low viscosity, but as soon as you start applying a force, then the viscosity is higher. So it has a greater resistance when you apply a shear force. So look at the interesting patterns that arise because of the movement of that subwoofer. And then they get it going with the high-speed camera. Kind of interesting shapes. Hopefully they'll show us the high-speed footage here in a second. All right, here we go. It almost looks like an animation, right? But it's not. This is the actual footage. It looks fake. But what's happening is that as the subwoofer is moving, it's applying a shear stress to that liquid. And so the liquid's viscosity is changing as the force is applied to the liquid. In the lab next week, we're going to deal with this cornstarch water mixture so that you can get kind of a tactile experience of what does it mean when a fluid is non-Newtonian. So those are a couple of video clips. Now let's go back to these definitions. A non-Newtonian fluid could be a shear thinning fluid. And so in a shear thinning fluid, what happens is when you apply a shear stress, then the viscosity decreases. So ketchup is an example of that. If you've ever pounded the back of a glass ketchup bottle, what you're doing is you're applying a shear force to the liquid, and temporarily the fluid becomes less viscous because of the force that was applied. That's a shear thinning fluid. A shear thickening fluid, which is what we just looked at with those previous two YouTube videos, is where the fluid becomes more viscous as a shear force is applied. So this graphical illustration is that a Newtonian fluid is not affected. Its viscosity doesn't change depending on what force is applied. But a shear thinning fluid becomes less viscous as the force is applied, whereas a shear thickening fluid becomes more viscous. So I'll give you a cornstarch and water mixture in lab next week and a spoon. And if you stir the spoon slowly, then it's easy to stir. But if you try to suddenly move the spoon really quickly through that cup of the liquid, then the liquid resists the movement. So it's kind of an interesting experience that we'll look at in the lab next week. We are out of time. We're going to have to talk about the gas laws in class on Tuesday.